So today we'll talk about two topics, vehicle production costs and total costs of ownership. So this is going to be thinking about, for the automaker, are we able to have a decent understanding of essentially how much it costs to build an electric vehicle and how that might change over time? And then the total cost of ownership is this type of analysis where we try and figure out how much money it would cost you to own and operate an electric vehicle sort of over its lifetime. And importantly, the reason why people do a lot of this analysis is to think about how the total cost of ownership, which is also known as the TCO, how the TCO of a EV compares to the TCO of a gas car. Okay. So to start off, production costs. Okay, so we've talked about some of the similarities and differences between electric cars and gas cars. So cars, these sorts of cars in general have been sort of mass produced for well over a century at this point, right? So we can really think about the era of the Ford Model T, which is the start of the assembly line. So when we think about this kind of process, right, there's dozens of different automakers. This is a really competitive market. This kind of production process has been sort of really well refined, and those costs are pretty well understood. And so when a lot of people talk about doing analysis of production costs, like this kind of thing is more sort of set in stone, and a lot of the room that you have to play with in figuring out the costs have to do with the production of the battery and of the motor, right? These are the two sort of more novel things. Obviously, there's like things about the car design that might change a little bit, with this different technology, right? You don't have to have an engine in your car anymore. So these are all things that will affect some of these production design decisions and therefore the costs. But again, this form factor has been well developed. So you wouldn't expect this sort of thing to change all that much as you change from a gas car technology to an electric car technology. So when we look at the sort of main difference here, a lot of the sort of direct and indirect costs end up translating sort of directly. There's this part of it where you might remove some of the combustion engine related content. And so this might be something like your engine, for example, which you wouldn't need in an electric car, right? And so when you go to an electric vehicle, so if this is the gas car costs and this is the electric vehicle costs, you do get to subtract a little bit of that stuff away, but then you have to add in all of this new stuff, right? So this is the really big one, which is mainly the battery pack. And then, as I was mentioning, the other part that you can maybe play around with, all the power electronics and the motor. This here is the difference in indirect cost because of volume, and we'll talk a little bit about that in just a moment. But this is sort of one estimate of the sort of difference in cost to produce an electric vehicle here compared to producing the gas car here, right? And so to the extent that these sort of boxes can be decreased, that's where you're going to be able to try and catch up with the old gas car technology. And because the remainder of it is kind of really well developed, it's unlikely that this stuff will get shifted too much. Okay. So thinking about sort of that portion of things, when we talk about the supply chain for electric vehicles, a lot of times people take this as sort of an analogous to the battery supply chain. Okay, and so you've got your raw material mining, the cell manufacturing, assembling the modules and the packs, and then sort of building the vehicle itself. And then these latter stages having to do with selling the vehicle, services to the vehicle, and then component recycling. So the sort of main areas to reduce costs, right, are going to be amongst these sort of different steps here. If we look at the material supply chain, it might look something like this. There are different ways that the supply chain is categorized. We have talked about some of these things for certain materials, like you have conflict minerals, right, with cobalt. And so that's shown here. They have this particular chart categorizes these things into these like risk categories. So the red ones are extremely risky, the orange ones, high risk, lighter orange, medium risk, and yellow as low risk. So depending on the types of materials that you'll be using, you could be sourcing from things that might be sort of low risk. This might be like lithium from Australia versus something like high risk materials, which would be cobalt coming from the Democratic Republic of Congo in Africa. And you can see kind of how the movement of these goods will change or will form the supply chain sort of throughout the world. A lot of the sort of manufacturing, for example, of the raw materials happens in different areas from where those materials themselves are mined, which is why you see these sort of chains being formed. Okay, any questions about any of this? Yeah.
Talk about the sustainability of mining. Are you concerned at all that in the future the supply of these minerals is going to
Yeah. So there's this whole sort of field of study where they look at resource adequacy and resource availability. Generally, when we think about this in an economic sense, it's not so much that the supply of the material kind of runs out, it's that the price of it gets really high. So you can think of this kind of in the same way as we think of like fuel resources, right? So for oil, for example, there's some kind of reserve that is sort of scattered throughout the world, and we can tap into that up to a certain point. We know that there's like a finite amount, right? And maybe we say, okay, if we use it like we do today, that would last for another 100 years, something like that. But in reality, what would happen is you get to materials that are like harder and harder to produce, and the prices go up, and then no one kind of wants to use that anymore, right? So imagine, would you still drive your car if gas cost $100 a gallon? Probably not. So, so we're not gonna run out of materials, but things could get to a point where you could have sort of economic infeasibility. But to go back to kind of the point of your question, right now, I think we're at a stage where we're nowhere kind of near that. A lot of the costs are actually going down because we're finding more reserve resources. We're getting better at doing a lot of the mining processes. I don't actually know the numbers behind those reserves that exist. Actually, someone else will have a guest speaker who will know a lot about that. But I would say it's not kind of an immediate worry for now. Okay, good question. Anyone else? Anything about this? Okay. So battery cost breakdown. I wanted to give kind of a couple different examples because people have looked at these breakdowns at sort of different points in time. And also there isn't always kind of a consistent consensus about the size and components of these breakdowns, and some of the different categories might differ in different people's analyses. But this should give you kind of a rough sense of what this looks like. So here This is the cells, and then you have things like power electronics, the housing, temperature control, overheads, margin and warranty, right? And so some of those things are going to be categorized differently. Like here, this includes pack components, which actually might be included in some of these guys over here. But they do have similar things like overhead, margin and warranty, and labor. And you can see the breakdown here as well. Again, the details of these are really difficult to measure accurately. So a lot of times getting this information from producers or from automakers is very difficult because it's often confidential and competitive information. But actually, even if you could get them to, tell you what the costs are, it might be kind of difficult for them to accurately sort of break these down into their sort of constituent parts, right? And also the 1000th battery would have maybe a really different cost breakdown compared to the first battery that they produce. And we'll talk about that concept in just a second. Yeah, and so these are coming from a number of different studies. And you can already see that there is sort of substantial variation in a lot of these costs, right? And so generally people say about 50% for the cell, so you can kind of see that here if you combine some of this, and you see here. And then the breakdown for the rest of the battery is still has quite a bit of variation to it. Okay, any questions about this breakdown? Okay, so how can we get the costs of these things to come down, or how do we know that some of this stuff has already come down? Right, we've talked about, at the beginning, in the early 2010s, right, we were on the order of like $500–600 per kilowatt hour, and now we're fairly certain we're under sort of this $130 per kilowatt hour. And so one of the things that happens is known as economies of scale, which basically the more you build, the cheaper it gets. So the sort of formal definition, right, are cost advantages that increase based on the scale of your operation. So why does this happen? As you scale up, if you are doing some sort of bulk orders, you can get large discounts, right? You can think about what it would mean to buy sort of 1 unit of something versus buying something at wholesale, right? This is why things are cheaper at Costco, because you get to buy a lot of them as opposed to just one of them, economies of scale. Managerial specialization. So if you're hiring people to do certain tasks, right? If you're at a really small operation, one person might be responsible for task A, B, C, right? They don't have as much ability to specialize, but once it gets really big, you might have one person sort of just dedicated to task A and one person just dedicated to task B. They get sort of better at it. And so you get some economies of scale that way. Financial scaling, this is a big one. So you get better interest rates when you're borrowing money. You can think about, okay, like what is the interest rate for borrowing money with your credit card versus if you were to borrow money to buy a house, right? This is kind of the same idea. The interest rates get a lot better when you're borrowing sort of more money. Marketing, so spreading costs of advertising, and then technological, this is returns to scale in production. All right, any questions about economies of scale? The other one, the other concept is a little bit sort of more nuanced. I think hopefully most people have heard of this before. This other one is kind of related in a sense. These are known as learning curves, and to some extent, economies of scale will kind of fall into this. But learning curves are actually a more sort of theoretical concept that allows us to sort of figure out how as scale increases, that you can decrease some of the costs, right? And so it's the same idea. Technologies become cheaper with increased production. The more tasks is performed, the less time is required on each subsequent iteration. Okay, so these are all, so with economies of scale, you might be able to build like a very specific curve that has to do with the amount that you produce versus the cost of production. Here, there are a whole bunch of other factors besides that that can go into decreasing costs. So labor efficiency. There's like a common example you can do in the classroom that I'm not going to make you guys do, but you can hand out paper and make people build paper airplanes, right? And by the 10th one that you build, you're going to do it really fast compared to the first one that you build. You just get better at it. Okay, same idea here. Workers become more dexterous and mentally more confident. You have to learn all these shortcuts. This type of thing happens basically across anything that you build that involves labor. Standardization, specialization, methods improvement. This kind of relates to that thing I was saying with the manager specialization, but it can sort of go across the board beyond just sort of one position. Technology-driven learning, so automated production technology. So this can be for sort of production happening autonomously, where you can improve the way that it does the production. It learns how to do things better. You can do things like machine learning, for example, to make processes more efficient. Better use of equipment. Higher production leads to better exploitation of equipment. It's not only that, actually. So if you have a certain type of equipment that is performing a certain task at a certain scale, you might, as you scale up, decide to invest in like a bigger machine that does it better and faster and more efficiently, right? And so this is the type of thing that's going to happen as you sort of move down these learning curves. Changes in the resource mix, product redesign. As you redesign the product, you might design it in such a way that it complements your sort of production process better and more efficiently. Okay, and so there's just a whole slew of things that kind of go into making your process of production more efficient and cheaper. And a lot of times in the sort of analysis, okay, we'll see here that the equation for this kind of curve when you do analysis is actually like fairly simple. Okay, this might look something like this. So this is some kind of exponential curve, right? And so this equation just looks like this. Y equals the cumulative cost per unit. A is the cost of the first thing that's produced. X is the number of units produced. And B is your sort of learning parameter. And so you can imagine if X is 1, which means you've only got one thing, right? Then Y is equal to A. So that's the first cost. And then this will continue to decrease over time based off of your sort of learning parameter. And what this number right here, this B, this learning parameter, that number is meant to sort of capture everything from the last slide. Okay, it's just this number that kind of represents all of the things that decrease the cost per unit that you are observing sort of in the data. So in other words, so this is an example of a learning curve for solar photovoltaic. And here are the prices per watt of a solar photovoltaic module. And so what you can do is I can take these data points right here, 1976, 1977, and so on. Let's say I go all the way to the year 1990, okay? I can observe all of these data points, and then I can essentially plug it into this equation and then solve for B, okay? And that B value will then let me draw this dotted curve here all the way out to 1990, and then I can use that. And if I were to sort of extend that curve out, you could see how that relates to how the costs change over time. And you can see that it actually does a sort of fairly good job. And what we've found generally is that most technologies are going to follow some sort of learning curve in decreasing in the cost over time. And you can look at evidence of the cost changes to determine what that learning rate looks like for your specific technology. And so we can do kind of the same thing, for example, for electric vehicles, or for batteries. So here we can see the lithium EV battery. Sometimes it's also called the experience curve. So you can see the historical price of lithium ion batteries. So this is dollars per watt hour. And we can see how this has sort of fallen over time and how we might expect this to sort of go out into the future as you have sort of more and more electric vehicle battery packs being produced. Okay. So we can use these curves to essentially help predict what the future prices will look like. Yeah. M. Actually, it would be related to B, but it wouldn't actually be B. Yeah, you'd have to, I think this is just telling you, because I think B is usually like a negative number. It might be. I'm not entirely sure what the M's are representing, but usually your B will be negative. All right. Questions about this? Great. Okay, oops. Did not mean to do that, sorry. Well, I don't know why that's happening. Okay, so yeah, this is a sort of powerful tool that allows us to have some sense of what the cost might look like. And as we leverage these types of models to understand the costs related to batteries, you can kind of extend that, right, to understanding what the cost might look like for the entire vehicle itself. So if I were to hop back to this earlier slide here, you could start to have a better sense of how each of these boxes might change based off of their size in the learning curve, and therefore how this might compare to this. And a lot of times that's where these estimates, you might start to see some of these estimates coming up of like, oh, when experts believe that like this will be equal to this, right? Because with the learning curves, you can actually tell the point in time that correspond to drops in the cost for production. Okay. So that covers kind of the cost side of things facing automakers. So now we'll talk about the costs of ownership as it relates to sort of this new technology. And so this is much more oriented towards the consumer point of view in understanding what are the costs related to driving an electric vehicle. Okay, total cost of ownership, also known as TCO. there's this fundamental question, right, that we've kind of been skirting around. Is an electric car cheaper or is a gas car cheaper? And what does that even mean, right? So I could say, well, the electric car costs more to buy than a gas car on average. But there's also subsidies and incentives, and then electricity is cheaper than gas. How do I take all of these things into account? What about other costs associated with it, like maintenance, insurance? So the total cost of ownership is a way of trying to do a really sort of apples to apples comparison between these two technologies and make sure that you basically address all of the costs that are associated with owning and using each vehicle. So things like the purchase cost will represent only a portion of the TCO. And there's a whole bunch of other costs that we need to look at in order to do sort of a fair comparison. Okay. So common cost components to consider in a TCO. So obviously there is this purchase price, and then you might have associated interest, right? Especially if you are financing the vehicle in some way, and you'll want to be able to take that into account. The fuel, insurance, maintenance, repair. So this is the typical breakdown for the TCO of a new car bought in the US. So this isn't just for electric cars, this is for cars in general. And so here, this is essentially kind of like your purchase price and your fuel. So that these two kind of constitute about 3/4 of the total cost of ownership. And then you have some other portions that you can see here. Okay, so what do you guys think? So purchase price, higher or lower for gas cars or for EVs? Yeah, so yes. Well, let's suppose that you have the car for the same amount of time, right? So EVs generally are more expensive. How about for fuel? Cheaper, right? Electricity we know is quite a bit cheaper than gas. We'll look at that sort of explicitly in a second. Insurance. Does anyone have an idea if insurance is cheaper or more expensive for a gas car or an electric car?
It would depend on like the sportiness per se of the vehicle.
Yeah.
Like a Model 3 Tesla versus or whatever the sport one, probably an S.
Okay.
A Model S Tesla versus a Model 3 is
And
insurance varies.
yeah, so you're getting at this thing of insurance will be more expensive for like sportier cars because maybe there's a higher probability that those cars get into accidents. That's one thing. Yeah.
That's one of the reasons they're on insurance, so not all of the often driving habits. So
Yeah. Yeah. That's right. And actually, this is getting more and more popular, not just with Tesla, but with sort of insurance companies in general. They will basically ask to, in a variety of ways, you can get super complicated to like even installing devices in your car, or it could just be from your phone. But essentially, they gather more information about your driving habits and patterns to potentially give you discounts. So if you are like a conservative and safe driver, it would make sense to enroll in these things. But the opposite could be true in some cases as well, right? You could end up getting more expensive insurance if they find that you're like a crazy driver.
I would say that gas is more expensive. There's more things that go wrong with gas vehicles. There's just so many more components.
Yeah, possibly. That's one thing that you would want to think about if you're an insurance company. The other big thing to think about though is that if you're insuring a vehicle, the more expensive the vehicle is, then generally the more expensive your insurance will be, right? Because all else equal, say you both have like a 10% chance of crashing your car, well then I want a higher sort of premium for the one that's more expensive because it's going to cost me more to pay out that insurance, right? So a bunch of things to think about, and we're going to look at a couple examples of insurance, and I think that you'll see that the insurance companies aren't necessarily sure either. Okay, last one, maintenance and repair. What do you guys think? Cheaper? All right, I hear cheaper. Right, we've talked about this a couple times. Generally, the things that you need to fix have to do with are correlated with kind of the moving parts of the vehicle. There's a lot less in an electric car, so maintenance is generally way lower. Okay, so let's go into each of these and break them down. So vehicle purchase price. This is seems like the most straightforward, but actually there are a couple different things that you want to keep in mind. So we've talked about the MSRP before. That's the manufacturer suggested retail price. And so this is, if you generally go to like the automaker's website, they will usually have an MSRP as kind of the suggested price. This is a good way, kind of good anchoring number for consumers to keep in mind so that you don't get like ripped off at the dealership, right? Pre-pandemic and pre sort of chip shortage, right, that we talked about, a lot of times, if you go to a dealership, let's say at like a sales event, they have like on holidays, like Memorial Day sale, right? Oftentimes the listing price that the dealership gives you might be lower than the MSRP, right? And you're like, oh, this is a great deal because it's below MSRP. I think I want to buy this car. Nowadays, right, it's in the other direction. A lot of the listing prices, as we talked about, due to the chip shortage, is way higher than the MSRP. But then there's the actual transaction price, right? Because you go to the dealership and they say, I want X dollars for this car. And you're like, no, I only want to pay Y dollars, throughout the all-weather pads or whatever that you're charging me like $2,000 for, right? And so there's a difference between the MSRP, what the dealership says they list the price at, and then what you actually pay, okay? A lot of times in the research world, the easiest thing to get is the MSRP because that's kind of uniform everywhere, right? Some people will even use they'll collect data on dealership prices, which might be a little bit more accurate than MSRP because it's a better indicator for sort of the bias of prices away from MSRP in the market. And ideally, we would want the transaction price, but that's the hardest to get, right? A lot of times that data is just not available. All of this kind of stuff refers to nuances having to do with things that you would have to negotiate at dealerships. But there is this different model, right? With Tesla, they don't have dealerships. Whatever they advertise is essentially what you get, right? So this price that you see online, you click it, no negotiation, you pay that price and you're good to go. And that's good, right? Especially if you don't like haggling with the dealership. But there's also a drawback. Tesla also changes the prices of their cars constantly, and you don't really have a say in that. If you look at this image here, Model Y is listed at $48,990. Does anyone know how much the Tesla Model Y is listed at now on their website? Someone can look it up. Yeah. Yeah, I think so. Yeah, in the last 6 months plus, yeah, the Model Y has gone up by $10,000. So yeah, I mean, you know, the dealerships have their sort of dealership markup, and so does Tesla. You just don't really see it. Oh, why does that keep happening? Okay. So that's the purchase price. Let's talk about fuel. Okay, so we've talked about the price of electricity versus the price of a gallon of gasoline, right? And so you get your electricity bill over here, and then you have your fuel prices here. But these are not exactly comparable, right? I don't know what it means to compare like $5 a gallon to 25 cents a kilowatt hour. To do a direct comparison, maybe it would be better to do something like on a cost per mile basis. And so we can do that, right? So consider, so the average car in the US is about 25 miles per gallon. And let's say you have gas prices at about $5 per gallon, which is kind of what you see a lot these days. So how would I go from 25 mpg into the dollar per mile metric that I want? So we're going to go mpg going to dollar per mile. Pretty straightforward calculation. Let's go. I see what's in the numerator, the dollars. So I'm going to do $5 per gallon times the average car is 25 mpg. So I'm actually just going to flip that. 25 miles per gallon, so that these cancel out, and I'm left with dollars per mile. So this is equal to 20 cents per mile. Okay. So if you are driving around in California with the average car, you would be paying 20 cents per mile that you're driving. So if I drive to like Sacramento from Davis, like 10 miles, 10, 15 miles, right, that would cost you $2 to $3 to drive there on gas. Why are you doing this? Let me flip my slides in peace. Okay, so this calculation, right? Okay, we can do the same thing. So the important part of this is that there are sort of two pieces of information in the comparison between fuel prices that you need to know, right? And so one of them is the actual cost of the fuel, but then the other one has to do with the vehicle itself. And so the differential between a gas car and an electric car could be different if you're driving a really efficient vehicle, right? And so with a Toyota Prius that gets 55 mpg, you would then change this denominator. So you're dividing by a larger number, so the cost per mile will decrease. So in this particular example, it might drop to sort of less than half. Okay, so keep this number in mind when we think about on the electric vehicle side. You know, the average car might be way more expensive, but then it might get a lot closer if you're thinking about switching from like a Prius. Okay. We've also talked about the cost of electricity, the per kilowatt, or sorry, the per kilowatt hour rates that you might see, right? If you are public charging or if you are residential charging. So let's do a similar type of calculation. Okay, so similar type of thing. If the average electric car in the US is about 0.3 kilowatt hours per mile. So we're going to go from kilowatt hours per mile going to dollars per mile. We can do a similar type of calculation. So I have dollars on top. So I'm going to go 30 cents per kilowatt hour. And in this case, I can just multiply directly with 0.3 kilowatt hours per mile. Okay, so the kilowatt hours cancel out, and I get 0.09 per mile. So if you are paying 30 cents per kilowatt hour, right, in this particular case, then it would be the same as the Toyota Prius at $5 a gallon. However, if you're paying less for electricity, so if you are in SAC, for example, here we can see if I'm charging off-peak in the winter and versus in the summer, right? In the summer, that's 16 cents. So it might be half of this. You go from 30 cents to 16 cents. And if you're charging in the winter, going down to 9 cents, it might be a third of this. Okay, and so that's different. So this number will look different if I'm charging at a public charger versus at home in different areas. And so you have to keep all of these things in mind when you think about these TCO calculations. Does an EV cost more? Does a gas car cost more? There are a lot of assumptions or sort of parameters you have to keep in mind when you actually do that direct comparison. Okay, any questions about these calculations? Great. So we have this. Okay, the next bit is maintenance costs. So maintenance costs, as we've talked about, it's pretty sort of generally agreed upon that electric vehicle maintenance costs are a lot lower. We've talked about a lot of those reasons. Here, there's kind of a nice breakdown of sort of how much cheaper it is. And I actually tend to think that this chart itself is actually a fairly conservative one. I think it could be lower than even half of the maintenance, right? And so anything related to the gas engine drivetrain is going to be sort of non-existent. In addition, the brakes last a lot longer because you have regenerative braking. If you are talking about a car that drives 150,000 miles, in this particular case, when I'm looking at a ICE vehicle compared to a fully electric, that's a 4 cent per mile savings. Over 150,000 miles, that's a savings of $6,000. So fairly substantial, and you could easily see that number being quite a bit higher. This is sort of very average numbers and conservative average numbers. Okay, last one. insurance costs. So a lot of online calculators you can look at to compare prices between gas and electric. And so we can see some examples here. So average price, average insurance for electric vehicles compared to the average price for gas cars. So in here, they're showing that electric cars are generally more expensive. However, and same with this one in this chart that you can see. But even in the exact same example here, they have the Kia Soul, the gas car version versus the electric. They're saying the electric is 1.23 times more expensive, but then with this online calculator, they're showing the same car being cheaper than the gas one. So I sort of scoured through a bunch of these, and there's pretty big inconsistencies between basically rates that you get from one company versus another. So definitely, I don't think that from the insurance standpoint, there's a really clear place for which one is cheaper at this point. Okay, any questions about insurance? Okay, let's do a quick 5-minute break and we'll reconvene. So when we think about calculating the TCOs, one of the things that we're keeping in mind is that you have like an upfront thing, right? This is the purchase price. And then you have things that kind of get amortized over time, which have to do with your fuel costs. So we can't really talk about doing this sort of comparison over time without talking about something known as discounting. Okay, so there is this concept known as time discounting, which describes the preference between the value of consuming something today versus consuming something in the future. Okay, so I asked this question on the poll. Okay, so all right, who wants $100? Everyone wants $100. All right, so volunteer. Anyone? All right, yes. I'll think about it, depending on how you answer these questions. So you can stay there. You don't have to come up. Okay. So if I were to give you $100, would you rather have that money right now or later? Right now. Okay, why? Because you need gas money. Well, you're gonna need gas money later too, right? So why not? Okay, it's worth, okay, why would it be worth more in the future? So it's worth less in the future. Yeah, exactly. Okay, great. So like, so you have this like internal calculus, like, okay, I want this $100 now because it's worth less in the future. In fact, you could, let's say if I were to say $100 now versus $100 1 year, you could take that $100 and you could do the same thing, right? You could stick it in a bank account and get like a little bit of interest, and you'd still make more money than if I gave it to you later. Okay, so this is known as time discounting, and we can try and measure your value. Okay, so I'm going to do that right now. Okay, so all right, so real simple, $100 today, $100 1 year from now. Which one do you pick? All right, $101 1 year from now, or $100 today? Today. $105 1 year from now, or $100 today? Still today. All right, 110, 120. 200. Okay. All right. We're just fine. Okay. So the way that we discount money is we do the future value of money, FV, divided by, right? We're dividing because the future is worth less. So you want to make it smaller. So 1 plus my discount rate to the number of periods in the future. So in this case, it's just 1 year, but we'll say T here. So for you, you said $200. Okay, so 200 divided by 1 plus R. Okay, this is just to the 1 here. So for you, this is equal to $100 today. So this is like, it would look like this. Okay. So if I were to rejigger this, I could multiply here, divide by 100, right? So it would be 1 plus R is equal to 2. So R is equal to 1. So you would have what we would call is a 100% discount rate. It's a little unusual, not usually that high, but it like depends on the situation. And in fact, like sometimes we try to elicit discount rates by like asking people, which as we see is not always like the best thing to do because like, oh, it's a hypothetical, you know, okay, you probably won't actually get that money. So you could just say kind of whatever, right? But for individuals, the sort of average discount rate is usually on the order of like 5 to 10% ish. And then for businesses, they typically have slightly higher discount rates. They have the availability of like sort of better investment opportunities. And so they would be more hesitant, right? Unless you can guarantee sort of higher returns. And so generally businesses will have something on the order of like 10 to 20% discount. And this sort of thing can change in different circumstances. Yeah. My future value? Yeah, inflation's pretty high these days, isn't it? I'd probably go like, I don't know, like 100, I would say for me, I'd probably do like 130, 140, something like that. These kind of questions, yeah, it's tricky. Like your answer can also change, right? So if I were to ask you the exact same scenario, but just change the magnitude of things. All right, so you ready? So $1 million today, $1 million next year. Okay, $1 million today versus, let's say, $1,050,000. 150. So you would take that 50K in 1 year. All right, so let's see how this changes. Yeah. So you get an extra $50,000. Yeah, you do that? Okay. So now your present value is 1 million. So 1 million equals 1,050,000 over 1 plus R to the 1. All right, someone run this for me. We're gonna see your discount rate drop like a rock.
Yeah.
What?
5%.
5%? Yeah, right. Okay, yes, because it's, yes. So this is, so R equals 5%. Okay. Yeah, so I wouldn't take it at that low because, right? Like, I bet that I could make more than 5% if I just stuck this into like an index fund for a year. I bet I could make like 100K, right? But it's, no, but right, if this is, you know, the like magnitude of the money is like making you change your mind. And people like you don't need to be a rational actor. And I'm not saying that you're irrational, right? Like people have different needs and sort of risk tolerances for money. And so this is perfectly reasonable, right? We said 5% is kind of the range of sort of a lot of average people's value of this. Okay, so let's think about this concept as it relates to doing these TCOs, right? So it's the same thing. For the upfront stuff, we consider that more important, right? And so spending more on EVs and then saving money on electricity later is kind of generally valued less than paying less upfront and then paying more sort of gas costs in the future. And so we need to, in order to incorporate the time discounting, this concept that people generally prefer to have more now, you have to do these sorts of calculations when you figure out the TCOs, and therefore allow you to do these sort of apples to apples comparisons, taking into account the fact that people think this way. Okay, so okay, as I was saying, kind of this equation here, C or future value, whatever, it's written differently in different textbooks. I guess I use R here. You can use I as well. But generally, present value is equal to future value divided by this. You can do it the other way, where you calculate the future value by multiplying the PV by the 1 plus R. But the general way that I like to remember this, right? Future value will always get divided to make it smaller. Present value gets multiplied to make it bigger. So what discount rate should we use? There isn't just one sort of correct answer. Businesses use 10 to 15% discount rates. Regulated utilities use this 6% number. Generally, right, sort of the larger it gets, you'll have sort of higher and higher discount rates. Higher the risk, the higher the discount rate. Okay, so we're gonna do an example, but before I do that, any questions or confusion about this concept? Okay, great. So we're gonna compare two compact SUVs being sold by Volkswagen. On the left, you've got the Tiguan, which is the gas version of the sort of compact SUV line that they have. And on the right, the Volkswagen ID4, same type of segment size class, newly sort of released. This came out last year. Okay, and so thinking about all of those things that go into the TCO, there's this big list of things, and we have to kind of take all of this information and incorporate it together to generate kind of this one final sort of TCO number. Okay, so let's do that. Okay, so one of the ways that I like to do these calculations to sort of help visualize it is to make this sort of timeline. So I'll do something like this. So this is year 0, year 1, year 2, and so on and so forth. We'll assume that this car goes for 15 years. So this will go like this all the way out over to here. So you'll have year 15. Okay. So let's just kind of walk through all of these things and see how they kind of fall into this, this timeline. So the first one is the purchase price. And so in a lot of these sort of timeline plots, you can go positive and negative. But because we're only dealing with costs, they're only going to be sort of negative. So I'll have like a big down arrow here representing a cost. Okay. And so here, the cost in year 0 is going to be $26,295. Okay, every year we will drive 12,000 miles at $5 per gallon, and we know that the car is 25 mpg. So we did that calculation earlier, but it will end up looking something like this. So we have the per mile number, which you just multiply by the number of miles driven per year. But this calculation ends up being something like 12,000 times 1 gallon. Okay, 12,000 miles times 1 gallon per mile times per 25 miles times $5 per gallon. Okay, and so that'll be 20 cents per mile times 12,000 miles. So that should be 2,000 or 250. Is that right? 240, yes. $2,400. Is that right? $2,400. Okay. So in every year, if we drive that same amount, you'll have one component of your down arrow. Okay. And this will be 2,400. We also know that you have insurance rates of $1,500 a year dropping by $30 a year. Okay, so this will be another 1,500. And that will be slightly smaller the next year. And then slightly smaller still the next year. Okay. And then lastly, there's a maintenance schedule. So let's see. Twice a year, we have $100 each time. So this will be another $200 that will always show up. And then every 3 years, we have an air and fuel filter change. So in year 3, I have this $200 and an extra $200 for the air and fuel filter. And then out in year 5, you'll have all of this stuff plus this extra $800 here. And then once over the lifetime of the vehicle, you'll have an extra $1,000. So that's on top of like everything else. Okay. So if you wanted to do the TCO undiscounted, I could just add up all these numbers and get an answer. And that would be sort of your undiscounted TCO, which doesn't take into account the fact that people think about, this time value of money. If you do take into account, it's a little bit trickier, right? I have to take this sum. Let's say this is X. Okay, and so here I would divide this by, so our discount rate is 5%. So I would divide this by 1.05 to the first power. And then for the next year, I would add all of this up. Let's say this is Y. And then I would do 1.05 squared. And then for year 3, same thing, I would add all of this up. Let's say this is Z, and that would be Z divided by 1.05 cubed. So you would go through this process in order to calculate the discounted value of the costs in each year. And then you could sum that all up to get your sort of present value of your TCO. And that's kind of the discounted TCO that represents a value that incorporates this discounting so that you can capture the way people think about the costs over time. And this is probably a much sort of fairer comparison in the sense that when you do a comparison between a gas car and an EV, people will be doing some kind of like mental discounting when they think about a lot of these costs. Okay, so if you do that, you end up looking something like this. And you can, you can do what I was saying here, where I discount each of the sum of these costs to get at all of the costs over time, and add that all up. So the TCO without discounting is going to be higher than your TCO with discounting. And so for the gas car, we can see it's 88,245 for the TCO, and the discounted cost is 69,440. Any questions about this? Okay, so do you guys think that the difference between the TCO discounted and undiscounted will be bigger or smaller for the EV? The relative size of that difference. You're doing this, I don't know what that means. Smaller, okay, and so explain your like rationale. Yep. Yeah. Exactly. Exactly. Yep. Exactly. And so we'll see that as we do this calculation. So actually, I guess I'm going to not run through all of this, but it's the same type of thing. But this actually allows, we can do a couple other things. In this case, you might actually have a sort of positive part because I'm including like a rebate for California and then a $7,500 tax credit, which is like an arrow that goes up if it's positive. And then same type of assumptions, but all sort of oriented for the electric car. So still driving 12,000 miles per year. In these comparisons, you might think of trying to compare like the same behavior for the same driver, if they're like thinking between two cars, or if you're thinking between two cars, you could do this kind of analysis. Insurance rates, and these are rates, these are kind of real rates that I basically tried to grab on some of these online calculators. And then a pretty different maintenance schedule, right? It's a lot lighter compared to the gas car. So you can take all of these things, run it through this kind of timeline model, and it would look something like this. So in this case, you actually end up having a positive arrow because of the tax credit. You would actually make money because of the credit that you'd be receiving from the government in this case. And we can see, all of the discounted values. So the differential with the rebates is only 10,000 as opposed to, right, and when we saw it here, that's almost a 20,000 difference. Okay, so the total cost, 88K, 69K for the discounted. So here, so forget this part for a second. With the rebates, both the TCO and the discounted TCO, the undiscounted TCO and the discounted TCO are both smaller than the gas car, right? We can see total cost is 66K, total discounted cost is 56 compared to 88 and 69. So this kind of harkens back to what I was saying before, right? We can see that the car is more expensive up front, but over its lifetime, this is already beating its like most comparable vehicle on the gas technology side. Okay, what about without rebates? So when you do this calculation, you can do the exact same thing and just take out this minus 7,500 as well as the $2,500 tax rebate. And you can see it's a lot closer actually. So this is 10K more on the undiscounted version and slightly lower than 10K more on the discounted version. But in fact, this is still lower, even without the rebate, this is still lower, right? So compared to the 88K and the 69K. So in this case, the EV over its lifetime, usually we're gonna think of the discounting as a way of making the fuel savings a little bit less. But even with discounting and without rebates, it's actually cheaper. Yeah.
So we assume the 15-year life cycle or like time.
Yep.
Calculation. I'm just curious to have a sense for like what would a consumer typically consider like the time over which they would think about their money. Like obviously, like if you're really good about planning, 15 years, you'd be like, okay, I can think about cost of years, but like the average person might not necessarily think that far.
That's a good question. I think for a lot of sort of average consumers think about these things in like 5-year chunks. So usually, I think, so when you do, we found that for a lot of consumers to think about this in sort of a back of the envelope way, they'll try and think about this in like a 5-year time chunk. But on the other hand, actually, if you have them kind of sit down for a second and actually think about the sort of math of it, it's pretty common for them to go a full-on sort of 12 to 15 years, which is kind of more what you'd expect with the lifetime of the vehicle. Yeah, good question. Because when we're talking about discounting, this is taking into the sort of perspective of what the individual consumer is thinking about. And so if they don't consider the lifetime of the vehicle, they might ignore, right, everything to the right of this and just think about the first 5 years. And you could do that calculation and see, okay, if they only thought about the first 5 years, would it still be cheaper? And I'm not entirely sure. Let's see, probably, I'll do a quick mental math thing here. That's about 8K, 46 minus 5. So that's like 41. So in a time, I don't know how close it'll be. So 41. So this would be let's say plus 15K. Oh yeah. So even at a 5-year interval with the subsidy, the gas car would definitely still be more expensive. It might flip, it'll probably flip-flop if you take the subsidy out. Yeah. So even shortening the time horizon, actually the electric car still seems better in this particular example, right? This is a artificially constructed example. I didn't actually know what would happen, but you can kind of futz around with considering different types of cars and seeing whether the sort of math still holds up, that the TCO would be sort of better or worse in certain cases versus others. Okay, so, in this particular case, we do find the EV is cheaper, but there's like a whole bunch of assumptions that we made to calculate the TCO, right? So things like how many miles they drove per year. So 12,000 miles is actually about the average mileage that an American drives in 1 year, but there's a pretty sort of large distribution. Some people drive as much as 15, 18, 20K a year. Some people drive as few as a couple thousand miles per year, right? And so the EV will look better the more miles there are, right? Because the fuel savings get bigger and bigger the more miles that you drive. But then conversely, if you drive fewer miles, it'll take you sort of longer to essentially make your money back by the fuel savings, right? Gas prices in this example, we assume that they were $5 per gallon. It's not too long ago that they were $3 a gallon, right? And so do we expect gas prices to remain that high? What if you assume that they were $4 or $3 per gallon? How would that affect the sort of math behind this? Same with electricity prices. There are a lot of special rates that exist for electric vehicles. What if you switch to those or better rates came out? What if you suddenly had to replace the battery in the EV? Like there are other bits of the maintenance that we assumed, okay, you just have these regular scheduled maintenance. What if you have, the sudden thing where you have to replace like a $20,000 battery? How would that affect the calculations? And so, the TCO analysis, there's a lot of parameters that affect all these costs, and you have to be careful about how robust your assumptions are to these things. Generally, we'll start to come to a place where even as you change a lot of these assumptions, like you still consistently see, let's say the EV being cheaper than the gas car, that's when you have sort of a lot more confidence that in general, sort of no matter what the conditions, the technology will end up looking better. And so you still have to kind of explore that right now to see if those comparisons are coming out better for gas cars or for electric vehicles. And okay, so the last thing that I'll say about this, we're going to get a lot more into some of the nuances behind consumer preferences and the way they think about why they buy vehicles and the sort of decision-making process behind that. This is actually a kind of controversial topic in the research world, because there's a lot of people who do these kind of analyses and they're like, oh, the TCOs are better for EVs, like people should just buy EVs. But like how many car buyers actually like sit down and do this kind of calculation, right? Probably none of them, or very few. And so the idea that the TCO is an accurate representation of the sort of decision-making behavior of consumers, you should, we can probably not go so far as to say that. And we'll again look at some more sort of nuances behind these decision-making processes in a different lecture. So we'll think about what factors might influence those purchasing decisions besides just, right, the cost of the technology. This is probably still a sort of good proxy representation of issues related to cost. And so as TCOs look better and better, I think you can use that as this sort of proxy that people understand that the product in general is cheaper. But we'll delve into all of these other factors that they think about when they buy a car as well. Okay, so that's all I have for today. We're going to end a little bit early. Yeah, thanks everyone. The second assignment has been posted. So that will be due end of the day, Wednesday next week. See you all on Wednesday.
That makes sense.